Okay, we will proceed now, and we will be hearing the staff presentation, and I understand Dr. Noland, you're going to introduce it. This is a CMD 17M64. Over to you.
Thank you. Good morning, Mr. President, members of the Commission. My name is Dr. David Newland. I am the Director General of the Directorate of Assessment and Analysis. Here with me today is Ms. Yolande Ackel, Director of the Probabilistic Safety Assessment and Reliability Division, and Smain Yaloui, a PSA technical specialist from the same division. In addition, we have other CNSC specialists and regulatory program staff to respond to any questions that you may have. The purpose of today's presentation is to provide you with a high-level technical briefing on probabilistic safety assessments, and in particular, a status update for the Whole Site PSA. The presentation will focus on some general aspects of PSAs, CNSC staff's initiatives to improve regulatory knowledge in the area of Whole Site PSA, including international collaboration, and lastly, a few points about OPG's Pickering pilot project, which you have just heard about. I will now pass the presentation over to Ms. Yolande Ackel. Thank you.
Thank you, Dr. Newland. Good morning, Mr. President and members of the Commission. My name is Yolande Ackel. I'm the Director of the Probabilistic Safety Assessment and Reliability Division, and I will be starting the presentation today by providing a brief background about the subject. Then I will turn it over to Mr. Yalawi to give a summary of the PSA approach, a description of CNSC safety goals, an update of CNSC staff involvement in the area of Whole Site PSA, including the international collaboration, and an update on the Whole Site PSA, including OPG Pickering Whole Site PSA pilot project preliminary results. An overall summary and conclusion will then be provided by Dr. Newland. This slide provides the definition of the probabilistic safety assessment and its aim and application, its main application. PSA is a systematic approach that complements the deterministic safety analysis by answering the following three questions. What can go wrong? What could be the consequences? And what is the likelihood of such consequences? This is defined as the risk triplet, which include the characterization of the set of events that can happen, their consequences, and their likelihood or probability of occurrence. PSA complements the deterministic safety assessment by integrating information about plant design, operation, component reliability, and human actions. The main applications of the PSA are identifying plant vulnerabilities and safety improvement opportunities to support plant modification and upgrades for the refurbishment projects and periodic safety reviews, the PSRs. Plant configuration management, input to maintenance planning, input to the risk-informed decision-making process, evaluation and rating of operation events, providing insights that can be used for training, preparation of emergency operation procedure, and accident management. As per regulatory document Reg 2.4.2, the licensees are required to conduct Level 1 and Level 2 PSA, consider both internal and external events, update the PSA every 5 years, perform uncertainty, sensitivity, and important analysis. The uncertainty analysis provide the mean, median, and the distribution percentiles of the PSA results. The sensitivity analyses provide the impact of the analysis assumptions on PSA results. Important analyses provide the ranking of the initiating events, system structures and components, and human actions according to their risk significance. The last bullet here refers to the requirements for seeking CNSC acceptance of the PSA methodology before conducting the PSA. As a reminder, we would like to highlight that PSA is just one part of the safety analysis safety control area. This slide is about the regulatory role of the Whole Site PSA. Whole Site PSA characterizes the overall risk of the nuclear facilities at the site, taking into account the benefits from the emergency mitigating equipments, the EME, added as part of the Fukushima Action Plan. The scope of the Whole Site PSA includes the impact from both internal and external hazards on all reactor units and on other major radiological sources, such as the irradiated fuel bay that is at the site. The main goal of Whole Site PSA is to provide risk insights and understanding of multi-source interaction, inter-unit common cause failures, and human action dependencies. Multi-source interactions refer to the interactions between the radioactive sources at the site, including prior and post-accident condition, in order to identify the vulnerabilities of accident propagation from one source to another. Insights from the Whole Site PSA can be used to support severe accident management guidelines, SAMG, and emergency planning. As a reminder, a Whole Site PSA is regarded as a complementary safety assessment for quantifying the overall nuclear plant site risk, with the acknowledgement that this is a new and not yet mature methodology. Both the CNSC and industry are following the international developments to improve the methodology. This slide provides the backgrounds on triggers of the Commission request to OPG to conduct the Whole Site PSA. During the May 2014 Pickering hearing, the Commission noted that the PSAs were developed and the results expressed on a reactor unit basis. It was also noted that there were no established site-based safety goals that would account for the number of nuclear facilities at the site. As a result of this public hearing, the Commission directed OPG to submit a detailed risk improvement plan for Pickering nuclear power plant, which encompassed a combination of physical, procedural, and analytical improvements, and to include in the annual report the status of additional Fukushima-related actions and improvements identified through the probabilistic safety assessment, and a clear timeline for the development and implementation of a Whole Site PSA safety goals and PSA methodology. Work on Pickering Whole Site PSA is now completed. A summary of the preliminary results will be provided in our presentation, and you just have heard a more detailed presentation that was presented by OPG. Although the risk improvement plan is not the focus of this presentation, it is worth mentioning it to update the Commission of its status and its related issues. In May the 5th, 2014, OPG submitted the risk improvement plan as required for hold point removal. CNSC staff reviewed and accepted the submission. The immediate priorities of the risk improvement plan focused on the following important risk contributors, as the results show as being above the safety goal target. Pickering Pickering A, severe core damage frequency for internal fires, and large release frequency for internal fires, and Pickering A, large release frequency for internal events at power. Actions were identified and completed by OPG as part of the risk improvement plan. The most important of these actions include emergency mitigating equipment modifications, installation of passive autocatalytic recombiner, tie down of EME for high wind, installation of flood barriers. Annual updates are now provided to the Commission as part of the regulatory oversight report for MPPs. These improvements resulted in a significant risk reduction of internal fire, SCDF, and LRF results. I will now turn it over to Mr. Yalawi to complete the presentation.
Thank you, Mrs. Akel Yolande. Good morning, Mr. President and members of the Commission. For the records, my name is Smain Yalawi. I am a PSA technical specialist. And in the next few slides, we will provide you with a brief description of the PSA approach. PSA is conducted in 3 levels. The level 1 PSA analyzes the sequences that could lead to the severe core damage, where there is extensive physical damage to multiple fuel channels, leading to loss of core structural integrity. At this level, the focus is on the plant responses to different internal events, internal hazards, and external hazards. Building on the results of the level 1 PSA, a level 2 examines the containment response to the accident and assesses the likelihood of a breach in the containment boundary, leading to the potential radioactive releases to the environment. A level 3 PSA assesses the off-site consequences, which could include both health and economic impacts. As indicated in the arrow above the figure, the uncertainty increases going from the level 1 to the level 3 PSA. Uncertainties in the level 3 PSAs are mainly due to meteorological data and weather conditions, wind direction. As we can see on the diagram, consequences could be different if the wind blows in one direction or in the opposite direction. Atmospheric dispersion model, the population distribution around the site, the food consumption habits, dose calculations, and the efficacy of the countermeasures. CNSC regulatory documents on PSA, Reg Doc 2.4.2, and most international regulators do not require level 3 PSA. However, off-site consequences could be completed using deterministic methodologies such as the CNSC 2015 study of consequences of a hypothetical severe accident, in which the source term is just postulated. We will now provide an illustration on how the level 1 PSA is constructed. Level 1 PSA begins with the identification of a set of initiating events. Remember, the first question was, what can go wrong? An initiating event is defined as any occurrence, including operator errors, equipment failures that have the potential to lead to core damage. These events are classified as internal events, internal hazards, and external events. The internal events are those events originating within a nuclear power plant. They include, for example, loss of coolant accidents, loss of power regulation, a pressure tube failure, loss of power, etc. The internal hazards include internal fires and internal floods, whereas the external events are those originating outside the nuclear power plant. They include natural events such as earthquakes and high winds, as well as man-made events such as transport accidents. In a CONDU PSA, there are over 100 initiating events that are factored in the level 1 PSA. The plant response is then modeled by considering the series of mitigating systems, such as the shutdown system and the emergency core cooling system, that must function to prevent the core damage. These systems are designed according to design codes, which include reliability considerations such as redundancy and diversity, providing different means for fulfilling a safety function, such as the control and cool safety functions. Each identified system is assigned failure probability that is calculated using a fault tree. A fault tree is a deductive logic diagram that depicts how a particular system failure can occur as a logical combination of its constituent components failures. It's a top-down approach. This enables the quantification of the accident sequences frequencies, represented in red on this diagram, which are then aggregated to calculate the core damage frequency. Level 1 PSA identifies thousands of accident sequences and failure paths, and which provides insight into design weaknesses and into ways of preventing core damage. We will now provide an illustration on how the level 2 PSA is constructed. The level 2 PSA builds upon the level 1 PSA, and we just say that the end result of the PSA has more than 1,000 accident sequences. Accident sequences from the level 1 PSA are grouped into a manageable number of initial plant damage states that will be used as an entry point to the accident progression event tree called plant damage states. A plant damage states represent groups of accident sequences that have similar accident timelines and initial status of containment, either intact or impaired containment, as well as the availability of containment subsystems that provide mitigating functions such as air coolers, hydrogen igniters, and filtered air discharge system. In a typical CONDU PSA, plant damage states include, for example, one plant damage state for one unit accident sequences, one plant damage state for multi-unit events, and one plant damage state for containment bypass. Accident progression event trees are then constructed to assess the capability of a plant to cope with the severe core damage accidents and to estimate the probabilities of various ways that containment failure may occur, leading to a release to the environment. An accident progression event tree, as shown in green in this chart, is an inductive technique that starts by postulating the occurrence of the plant damage state and proceeds through the accident progression. The logic of this tree is built by answering the questions about the accident phenomenology and chronology. Example, is the containment integrity maintained, yes or not? Is the corium debris retained in the calandria, as shown in the first figure on the left? Does hydrogen ignition induces gross containment leakage? Does the core concrete interaction occurs? This would tell us about the hydrogen production, for example. The end states of this accident progression event trees provides the release categories, characterized by the timing, either early or late release, as well as the magnitude of radioactive releases, such as a release higher than 10 to the 14th becquerel of cesium-137. The large release frequency is then calculated based on the release categories, and the strategy, the severe accident strategy, consists of retaining the molten core in the calandria vessel to avoid any core concrete interaction that would challenge the containment. This slide shows the PSA results and insights, as already mentioned in the presentation by OPG. PSA is not just about the numbers and probabilities. It provides valuable insights such as plant vulnerabilities, dominant risk contributors, significant human actions. As an example of PSA results, this figure shows the figure shown in this slide provides an illustration of the risk profile, which shows the contributions to the overall core damage from different hazard groups, such as internal events, seismic event, and high winds, for example. The figure on the right provides the breakdown of internal events, because internal events is just a hazard group, and shows the contribution from different initiating events. As we can see, the contribution from streamline break or pressure tube failure to the overall core damage frequency. PSA results also provide the contribution to risk from different systems. This allows the ranking of the systems by their relative importance and risk significance. The figure provided in this slide is just for illustration purposes, and generation of such charts, of course, is specific to each reactor. It shows, for example, that if the emergency water system is not available, then the instantaneous core damage frequency will increase by a factor of 1,000. This is the first bar of the chart. The emergency water system is the system that provides emergency makeup to the steam generators for decay heat removal in the event of a failure of feed water supply. PSA results can also be expanded to provide the ranking and the risk significance at the component level. We don't stop at the system, but also we can provide the ranking at the component level. PSA, therefore, provides valuable insights that can be used for regulatory oversight to focus on what matters to the safety. In this slide, we provide a summary of key messages about the PSA approach. It is a systematic approach which integrates information about plant design, operation, component reliability, and human actions. PSA provides information on the likelihood of accident sequences. It identifies dominant contributors to risk, such as initiating events, systems, components and structures, and human actions. It provides insights that can be used for training and preparation of emergency operating procedures. The banner here shows that the focus should be put on the safety instead of the probabilities, as PSA is a powerful tool for identifying safety improvement opportunities. In the next following slides, we will provide the definition and context for the CNSC safety goals and explain as to why the level 2 PSA results are sufficient for the purpose of protecting people and the environment. Because we started by showing the 3 levels of PSA, here we would explain why we stop at the level 2 PSA for the safety goals. CNSC established safety goals such that they are not dependent on the reactor power. They allow verification of compliance at design stage, which means that there's no site-specific data required. And also, they minimize the uncertainties in the assessment. We already mentioned the uncertainties related to the level 3 PSA. Setting the safety goals at the level 2 PSA by limiting the frequency of the radioactive release is sufficient for protecting people and the environment. This slide provides the basis and the rationale for the derivation of CNSC safety goals, which include, for the level 1, the risk metric is the core damage frequency. This metric includes the information regarding all event sequences leading to core disassembly. And limiting the frequency of such outcome serves the prevention principle of the defense in depth. For the level 2 PSA, 2 metrics are defined to prevent public disruption. The first one is the small release frequency, where a limit on the frequency is set for any release higher than 1 to the 15th becquerel of iodine-131. The rationale behind this safety goal is the prevention of temporary evacuation of the population. The second risk matrix is the large release frequency, where a limit is put on the frequency for any release higher than 1 to the 14th becquerel of cesium-137. And the rationale behind this safety goal is the prevention of permanent relocation of the population. Now we will address the rationale for the quantitative safety goals. During the Chernobyl accident, 1986, the radionuclides that caused exposure to individuals were mainly iodine-131 and cesium-137. This explains why we have set this small release frequency and large release frequency, accounting for iodine and cesium. 10 to the 14th becquerel of cesium-137 represent a small fraction of the Chernobyl accident release. This is less than 0.1%. Results from the Finland and Swedish Nordic nuclear safety research in 2007 showed that there's no large land areas are contaminated as a consequence of a release of 10 to the 14th becquerel of cesium-137. They also showed that the maximum individual dose at a distance of 3 kilometers is less than 10 millisievert. CNSC 2015 study of consequences of a hypothetical severe accident showed that for a generic release of 10 to the 14th becquerel of cesium-137, consequences can be managed effectively. This slide speaks to the comparison of PSA results against the established safety goals. As this is stated in the IAEA INSAG 8 publication in 1985, owing to its inherent uncertainties, the PSA should not be used in isolation to judge the safety of a plant. Nevertheless, a PSA can be of use as an indicator of safety. Therefore, PSA results should not be regarded as a pass-fail line. Aspects related to defense in-depth, safety margins, and regulatory requirements need to be considered as part of a comprehensive, risk-informed decision-making process. In this slide, we summarize the key messages regarding the safety goals definition and their role in protecting people and the environment. Setting the safety goal at the level 2 PSA is sufficient for protecting people and the environment. This is achieved by setting a frequency limit on radioactive releases of iodine-131 and cesium-137 to the environment. The small release frequency and large release frequency are established in such a way to prevent temporary evacuation and long-term relocation, respectively. Owing to uncertainties in the PSA, the safety goals should not be regarded as a pass-fail line. In the next following slides, we will provide an update regarding the staff's involvement in the area of Whole Site PSA, including our international collaboration. This slide shows CNSC staff initiatives, including the Fukushima follow-up. The first initiative was related to the revision of the existing regulatory framework, where the regulatory document on PSA was updated and reissued as Reg Doc 2.4.2 in May 2014. The revision specifically included multi-unit impacts, consideration of other radioactive sources such as the irradiated fuel bay, and the consideration of potential combinations of internal and external events. To reflect what happened in Fukushima, the combination of hazards of tsunami and earthquake. The other important initiative undertaken by staff is the organization of an international workshop on multi-unit PSA in Ottawa, November 2014. This workshop brought together eminent international experts, regulators, academics, consulting organizations, and industry to share experience on the topic of multi-unit PSA and site-based safety goals. A workshop summary report is available on the CNSC website, and the full report is available upon request. It is worth mentioning that the workshop report is used by many countries, and notably the IAEA, as a reference document in the area of multi-unit PSA. Another initiative is the involvement and active role of CNSC staff in two international cooperation projects pertaining to the development of Whole Site PSA and multi-unit PSA methodologies. The first project is within the Working Group on Risk, WG Risk, under the Nuclear Energy Agency, and the second one is with the International Atomic Energy Agency. The first project title is Status of Site-Level PSA, including multi-unit PSA developments. This project is within the Working Group on Risk under the Nuclear Energy Agency of the Organization for Economic Cooperation and Development, OECD. This project started in December 2015, and this is expected to end in 2018. The project has two phases. The phase one is led by Canada, CNSC, and this consisted of the preparation of surveys on member states' practices and research activities on site-level PSA, preparation of draft reports on specific focus areas, identification of technical topics for the phase two of the project. Phase two will be led by Germany, and this phase aims at organizing an international workshop on site-level PSA in July 2018 in Germany. This slide elaborates on the second project on multi-unit PSA with the International Atomic Energy Agency. This project started in November 2016, just last year, and is expected to be completed in December 2019. Phase 1 of this project aims at developing multi-unit PSA guidelines. This phase is just completed last month, November 2017. Phase 2 of the project consists of applying the guidelines developed as part of the Phase 1 to conduct a case study on a specific site with 2 pairs of reactor units, 1 old pair and 1 new pair of reactors. The scope of this project covers only level 1 PSA and include multi-unit events that can affect at least 1 pair of reactor units. But the scope does not cover, for example, other radioactive sources on the site. In the Phase 3 project, the proposed multi-unit PSA methodology and guidelines will be revisited to reflect the lessons learned once the case study is completed. After completion of the Phase 3, an IAEA technical document will be issued in 2019. It is worth to mention that OPG's methodology on whole site PSA will be included as part of the IAEA publication. The major outcomes from this international cooperation: further insights can be gained from the whole site PSA in understanding multi-source interaction, inter-unit common cause failures, and human action dependencies. There is also an increasing interest in conducting multi-unit PSA in different countries: India, Japan, Korea, UK, and US. As an example, US Nuclear Regulatory Commission is performing an integrated site level 3 PSA for the Whole site, comprised with multiple co-located sources of radiological materials. Korea, the regulator, and the industry started a multi-unit PSA project for Korea site, and this is aimed to be completed in 2021. UK, a multi-unit PSA is being performed by the UK ABWR PSA, Advanced Boiled Water Reactors PSA, as part of the site-specific PSA. India and Japan are also starting multi-unit PSA projects. Work is ongoing for international consensus on whole site PSA methodology. This slide summarizes the important key messages regarding staff involvement in whole site PSA. Staff took many actions following to the Commission request on whole site PSA. This includes the amendment of CNSC Reg Doc 2.42 on PSA and the organization of international workshop on multi-unit PSA, which is now used as a reference. CNSC staff have an active role in international effort to develop whole site PSA methodology and guidelines, specifically with the Nuclear Energy Agency and the IAEA. CONDU Owners Group COG methodology and the Pickering pilot whole site PSA will be included in the IAEA technical document to be issued in 2019. Now we will provide a brief update regarding the development of OPG's Pickering whole site PSA pilot project, as well as its preliminary results. More details were provided in the previous presentation by OPG. Before discussing OPG's submission, this figure provides an illustration of multi-unit PSA construct. How do we construct a multi-unit PSA? Let's just let's suppose a site with 2 reactor units, Unit 1 and Unit 2, as shown in this graph. The units are subject to 3 categories of initiating events. The first category is about events that occur at one unit and affect only the unit itself. For example, this event affecting only Unit 1 and effects affecting only Unit 2. These are called single unit events. For example, a unit forced shutdown, a pressure tube failure. The probability of having coincidental pressure tube failures in 2 units is highly unlikely. These are called mutually exclusive events. The planned response to single unit events depends on the success or failure of the unit mitigating systems as shown as described in the previous slide on the PSA approach, and can lead to the core damage. The second category of events is about events occurring in one unit, but which can affect the other unit. For example, a steam line break in Unit 1 can affect Unit 2, or a steam line break occurring in Unit 2 affecting the Unit 1. Such events could lead to the core damage in both Unit 1 and Unit 2. The third category of events is about multi-unit events, which can affect both units simultaneously. For example, a seismic event or loss of off-site power that could lead to the core damage in both, that can affect both units simultaneously, like the seismic events, loss of site power, that could affect both units at the time. And similarly, events affecting the shared systems could also lead to core damage in both Unit 1 and Unit 2. This is represented in red. Note that the shared systems between units present advantages, specifically in the condo design, by providing additional mitigating systems for non-reactor units, such as the inter-unit feedwater tie that provides feedwater to the boilers to the accident unit. When calculating the total multi-unit core damage frequency, caution should be exercised for not double counting the accident sequences in both units, as illustrated by the Venn diagram. This is the area shown in red. If we just count 2 times, then we will be double counting the area in red. As a note, multi-unit impacts are fully accounted for in the current condo PSA practice. This is why staff always caution that the site core damage frequency cannot be obtained by simply multiplying the unit core damage frequency by the number of units at the site. In this slide, we'll present the OPG submissions. OPG submitted their concept-level whole site PSA methodology in February 2014. This was reviewed and accepted by CNSC staff. OPG's Pickering whole site package was submitted in October 2017. The package included other supporting technical documents such as assessment of irradiated fuel bay and fuel dry storage impact on the whole site risk, and assessment and contributions from the different operating states such as full power and the shutdown state, and the operational states in between. In addition, and as part of the Fukushima Action Plan, OPG has completed the assessment of irradiated fuel bay structural integrity, conducted programs and procedures upgrades, including, for example, inclusion of multi-unit events in severe accident management guidelines, SAMGs, and the inclusion of IFB events in station operating documentation. This table shows the PSA, whole site PSA preliminary results for the severe core damage frequency. As we can see from the table, both Pickering A and Pickering B PSA results per hazard group are well below the safety goal for existing nuclear power plants of 1 to the -4. The table also shows that Pickering B results are lower compared to the Pickering A results, and this reflects the design differences between the 2 stations, specifically the inherent design improvements incorporated in the design of Pickering B station. The results are aggregated for all hazards on a per reactor basis, each hazard on a per site basis, and all hazards on a per site basis. Aggregated results include the Pickering A and Pickering B PSA updates results, as well as the periodic safety review modification, as mentioned by OPG. Aggregated site CDF is below the unit-based CDF safety goal of 1 in 10,000 years. This table now shows the preliminary results on the large release frequency, and we can see that the aggregated site large release frequency is below the unit-based large release frequency safety goal of 1 in 100,000 years. I will now pass it on to Dr. Newland to present the overall summary and the conclusions. Thank you.
Next slide. So in summary, CNSC staff are leading in international cooperation in the area of whole site PSA. A status update of OPG's risk improvement plan and its implementation is presented annually to the Commission as part of the NPP Regulatory Oversight Report. A concept-level whole site PSA methodology was submitted by OPG in February 2014, and this was reviewed and accepted by CNSC staff. As of yesterday, we have received the final results of the Pickering pilot project. Finally, now turning to the conclusions, PSA is a process that helps to gain risk insights and informs risk improvement opportunities. The primary focus of PSA is risk insights, and PSA results are not used as the sole basis for regulatory decisions. The preliminary results of the PSA show that the site-wide core damage frequency is less than the single unit-based safety goal of 1 in 10,000 years, and the site large release frequency is less than the single unit-based safety goal of 1 in 100,000 years. CNSC staff agree with OPG's overall results, specifically the methodology used to avoid the double counting of accident sequences. CNSC staff's assessment of this PSA is ongoing, and the results will be communicated as part of the regulatory oversight report. That concludes staff's presentation. Thank you very much, and we're available to answer any questions that you may have. Thank you.
Thank you.